Hello, everyone, and welcome to today's One World Mind seminar. It's my pleasure to introduce our speaker, Ethan Epperly. Ethan is a Miller Research Fellow in the Mathematics Department at UC Berkeley, and he previously received his PhD in Applied and Computational Mathematics from Caltech. He has been recognized for his work with finalist status for the Hertz Foundation Fellowship, Caltech's Thomas A. Tisch Prize for Graduate Teaching in CMS, Carey and Company Prize in Applied Mathematics, and Siam Student Paper Prize. Let's welcome him, and we're excited to hear him today speak on column subset selection, active learning, and determinantal point processes. Turn it over to you, Ethan.
Thanks, Kevin. Thanks for the warm um, introduction, and thanks for inviting me to speak here. So as Kevin mentioned, I'll be talking about column subset selection, active learning, and determinantal point processes. And I imagine this audience, probably many people know quite a bit about at least one of these things. And I guess my goal in this talk is just really to kind of provide an introduction to these three topics, kind of focused on a treatment that's going to show ways in which these different topics interact with each other. And my focus is going to be kind of more conceptual, and I'll be talking about a lot of other people's work and some of my own has really been in braiding these topics all together. And please, if I'm ever saying something that is unclear, stop me and I hopefully can clarify. All right. So to begin, we're going to be talking about subset selection problems in this talk, by which, at a conceptual level, a subset selection problem is maybe described as follows. So I'm given some data set of elements, and I want to pick a small subset of diverse elements which somehow represent the data set. So to kind of illustrate what I mean, let's think about a very simple subset selection problem. So here's a data set of 6 emojis. And we might say, if I wanted to pick a small number of emojis to represent this set, how would I do so? And to me, at least, it seems like natural. Well, half of the emojis have hard eyes and half of them have tongues sticking out. So say, let's pick one with hearts and one with its tongue sticking out. And so this would be a subset of elements. They're diverse, they're very different from each other, and somehow they give us a nice, concise summary of this data set. Now, of course, when we're going to do mathematics with data sets, we're typically not going to think of kind of visual glyphs as our data set. We're going to think of vectors. So we can indeed take a data set of any type and represent it by some kind of vectorization. So here I've assigned a vector to each emoji, and then picking a representative set of emojis would then become picking a representative set of vectors. Now, clearly, this is an easy problem to solve just visually when we have 6 emojis and we want to pick 2 of them. But if I say have a billion data points and I want to pick 100 of them or 1,000 of them, that's a much more challenging problem. Now, naturally, when we have a collection of vectors, it can be helpful to stack them together into a matrix. And this takes our data subset selection problem and reformulates it as a linear algebra problem or a column subset selection problem. So each column of this matrix corresponds to one of the data points. And we're now asked to select a subset of the columns that are going to represent this data matrix. And by represent in this case, I'm going to mean approximately span. So my goal is to pick a subset of columns where if I take their linear span, it's going to approximately contain all of the columns in this matrix. So here I've just taken this kind of qualitative notion of a subset of items which represent a data matrix, and I've made it more mathematical by replacing this word represent with approximately span. All right. So as I mentioned, this talk is going to be more conceptual. It's going to be about kind of big ideas and algorithms and how different ideas are connected to each other. But rest assured, this is a useful task in machine learning and scientific computation. So I just picked a small subset of representative applications. So for instance, you could do data selection for fine tuning. So you have a big data set, you want to pick a small number of data elements to fine tune your model. You can apply this to weight matrices in a model to compress a model. You can also use this for product recommendation. So if my data set is a collection of products, And I have a recommendation box at the bottom of the website. Which subset of items should I put into that recommendation box? But this is also a very useful problem, particularly the column subset selection problem in scientific computing. So there's some very beautiful work that uses column subset selection methods to localize orbitals for computational chemistry. There's another line of work that uses column subset selection to construct tensor decompositions, which are very useful in quantum science. And also, you can think of problems where you want to pick interpolation points or quadrature nodes, say in a rational approximation or other types of numerical tasks. And this can also be thought of as a subset selection problem. Which of all the possible points that I could interpolate or use for quadrature should I select? So again, this is going to be a more conceptual talk. I'm not going to really talk about any of these applications, but hopefully we can go forward with some sense that this is a valuable endeavor for downstream tasks. All right, so let me give you an overview of what the rest of the talk is going to look like. So I'm going to begin by talking about column subset selection problems. I'm then going to talk about volume sampling and the closely related idea of determinantal point processes. Then I'm going to describe an algorithm for column subset selection known as adaptive randomized pivoting due to Cordovez and Kressner. I'll tell you a little bit about active learning and active linear regression. And then I'll braid all of these topics together and describe how they're connected. And then we're going to use the connection between all of these ideas to develop improved algorithms. And then I'll show you how the improved algorithms work in some numerical experiments. All right, so let me begin by talking about column subset selection. So I'm actually going to do a little bit of a sleight of hand. So the popular term in the literature for this problem is column subset selection, but I'm going to actually immediately change to the problem of row subset selection. And this is fine because the columns of a matrix B are just the rows of B transpose. So these are basically equivalent problems, picking columns of B, picking rows of B transpose. And I'm just going to fix, for the rest of this talk, I'm going to pick rows. So let me give you some notation, which will be used throughout the talk. So A is always going to be a big data matrix of size n by d. And I've represented that matrix here. And S is always going to be a subset of the set 1 to n, which indexes a set of k rows. So S will always have cardinality k. And so I've shown here, if I pick 1, 4, 5, and 7, I've highlighted the selected rows of the matrix in yellow. And I can actually pull these selected rows out into a new matrix, which I'll call A sub S. So A sub S will always denote the row submatrix of A indexed by the set S. And indeed, I'll also use throughout the talk, whenever I take a matrix and I subscript it by some object, that's always going to refer to the submatrix indexed by whatever I've put in the subscript. All right. So as I mentioned, the subset selection problem for this talk is going to be given a matrix A in a subset size K. We're going to find a set S of rows such that the row submatrix AS approximately spans the matrix A. Now, every approximation to A that's spanned by the selected rows AS is going to take the form A hat equals W times AS, where this W matrix is going to be all of the linear combination coefficients. It's going to tell me how I'm going to approximate every row of A by a linear combination of the rows AS. Now, the best choice of this so-called interpolation matrix W is easy to find. Again, this is basically just a linear least squares problem, and its solution is given by A times AS pseudo inverse, where throughout this talk, this dagger is going to be the pseudo inverse. Now, I should mention, we're interested in subset selection problems in this talk. Many applications, we're just going to need the subset S, but this interpolation matrix W is going to be important for other applications. So for the algorithms we're going to be talking about, we're also going to be talking about how do we build this interpolation matrix W. All right, but kind of putting the interpolation matrix to the side for a moment, if we simply substitute this optimal choice of interpolation matrix into this expression for A hat, We can think of the subset selection problem as trying to find a subset S of k elements that minimizes the error of A minus A hat, where A hat is now going to be A times AS pseudo inverse times AS. Right. So is this formulation of the subset selection problem clear? All right. Hearing no objections, I'll continue. All right. So we're interested in trying to find the best subset of rows S as we can. And so it's very natural to ask, how good at spanning the entire matrix can any set of rows K be? Before we talk about algorithms, let's merely talk about existence or approximation quality. How good can an approximation of the form A hat equals W times AS even be? And this question has a very nice answer. So to begin, let me remind you of the Eckart-Young theorem, which states that the best rank K approximation, A, which I'll denote by A subscript K, is given by the projection of A onto its K dominant left singular vectors, UK. So the best rank K approximation is just UK times UK transpose times A. But this best rank K approximation AK is typically not spanned by any set of K rows. But fortunately, we can still get something. So there's a very nice existence theorem due to Deshpande, Rademacher, Vampala, and Wong in 2006, which states that every matrix A has a row set S of cardinality K, which spans a near optimal rank K approximation, in the sense that this A minus A hat, where A hat is this optimal W matrix times the row submatrix, the squared Frobenius norm of this quantity is always going to be at most K plus 1 times the best rank K approximation error, again, in the squared Frobenius norm. So this really says that the best the best row-based low rank approximation to A is at most a small factor of K plus 1 times the best rank K approximation. And for all the algorithms in this talk, we're going to be trying to find row subsets that achieve this optimal existence guarantee. And I should mention that this prefactor of K plus 1 is going to be optimal for a worst case matrix. So there exists a matrix for which no prefactor smaller than K plus 1 is possible. So in this sense, this is an optimal existence theorem for row-based approximations to a matrix. All right, so this is an existence result, and it's natural to ask, how could we prove this theorem? How could we find such a set of good rows algorithmically? So we want a constructive procedure to achieve the guarantees of this theorem. And this leads us very naturally to the ideas of volume sampling and determinantal point processes. Now, let me begin by telling you something about volume and why it's related to row selection. So there's a kind of a maxim that's really been around for nearly 30 years at this point, maybe actually probably more than that. And this maxim states that a good set of rows, a good subset of rows for our row set subset selection problem, is one that spans a large volume. And the volume here, the volume of a subset S of rows of A, is just defined algebraically to be the square root of the determinant of AS times AS transpose. And geometrically, we can think of this as a volume of a parallel piped bounded by sides given by the rows that are indexed by our subset. So the volume of a set of rows is the volume of the parallel piped bounded by the rows as the sides of this parallel piped. And this maxim states that if we want a good set of rows, we should pick one that spans a large volume. Now, on its face, it kind of seems odd. Why is volume related to this question of spanning a good approximation to A? But there's a clean way of seeing why volume is connected to this subset selection problem. So if I pick a bunch of small rows, well, then the volume is going to be small. And so these are not going to be good representatives of my data set because the data is not important. The row norms are small. So picking large norm rows is not enough. Because if I pick two large norm rows that are nearly linearly dependent, they have a very small angle between them, and they're still going to span a small volume. And this means that the data is not diverse. I'm picking two data points which are nearly the same, and that's going to give me a small volume. But the good case happens when we pick two rows that are both large in norm and not dependent. So they have a big wide angle between them. And in this case, they're going to span a large volume. In this case, the large volume indicates that each data point is individually important, and the data points are diverse in the sense that the angles between them are sufficiently large. So hopefully these kind of three pictures indicate why picking large volume submatrices is a good idea for solving the row subset selection problem. Now, unfortunately, finding a maximum volume subset of rows is an NP-hard combinatorial optimization problem. So we're not going to be able to solve this problem exactly, and there are several kind of different approaches we can use to get around this NP hardness result. One of the most beautiful is to relax this optimization problem of finding a maximum volume subset to instead a sampling problem of trying to select a collection of rows with probability weighted by volume. And it turns out that this sampling-based formulation of volume-based selection is tractable, at least in the sense of being polynomial time. So the algorithmic idea, which is also due to Deshpande, Rademacher, Von Paula, and Wong, is to pick a row subset S randomly with probability proportional to the squared volume of that subset. So throughout this talk, I'm going to use this symbol proportional to indicate a probability that's equal to whatever I specify up to some normalizing constant. Just say up to some normalizing constant, the probability is proportional to the squared volume. And this distribution on k element subsets is going to be known as the volume sampling distribution for this talk. And Deshpande, Rademacher, Von Paul, and Wong proved their existence theorem by the probabilistic method. So they proved that if I draw S from the volume sampling distribution, then the error of this row-based low-rank approximation is going to be less than or equal to k plus 1 times the error of the best rank k approximation. In particular, if the expectation is less than k plus 1 times the best rank k approximation error, there must exist a subset S achieving this guarantee. So we've now at least shown the idea behind the proof of this existence result for good subsets of rows. Right. So now I want to draw a connection between this idea of volume sampling to another idea. So I just want to first note for you that from this definition of volumes in terms of determinants, we can also think of the volume sampling as picking a submatrix S with probability proportional to the determinant of AS transpose. For those of you who are familiar, this might bring up a connection to another type of random subset, namely a so-called k-determinantal point process, where a k-determinantal point process with kernel matrix M is just merely defined as a random subset S whose probability is proportional to the determinant of the principal submatrix of M induced by the set S. And from the definition of a k-determinantal point process and the definition of volume sampling, it's very clear to see that volume sampling on A is the same as k-determinantal point process sampling on M equals A transpose. And this is a very nice connection to observe because determinantal point processes have been studied in stochastic geometry and probability theory since the 70s at least. So there's a wealth of mathematical knowledge about determinantal point processes that can be leveraged to understand volume sampling, and now vice versa. And I should mention there's a very nice survey 13 years ago now about determinantal point processes for machine learning. And I've collected a quote here, which I think really speaks to why determinantal point processes and by extension, volume sampling are valuable for subset selection problems in machine learning. So they write, The essential character of a DPP is that these binary variables, that is the probability that any individual element is contained or not contained within the subset, are negatively correlated. That is, the inclusion of one item makes the inclusion of other items less likely. The strengths of these negative correlations are derived from a kernel matrix that defines a global measure of similarity between pairs of items so that more similar items are less likely to co-occur. As a result, DPPs assign higher probability to sets of items that are diverse. For example, a DPP will prefer search results that cover multiple distinct aspects of a user's query rather than focusing on the most popular or salient one. All right. So hopefully, for those of you who know about KDPPs, the connection is useful to at least note. And there's a question, shouldn't M be AS transpose? Um, M is equal to AA transpose. And if I look at the the submatrix of M induced by S, this will be AS transpose. Hopefully that answers. All right. So this is a nice kind of computational strategy in principle, because it achieves this nice optimal guarantee. However, performing sampling from this volume or DPP sampling distribution is challenging computationally. So direct exact samplers will run in cubic time, order ND squared, which is very bad if I have a very big data matrix. And there are faster alternatives based on Markov chain Monte Carlo or very clever rejection sampling. But I still think it's fair to say that these volume sampling algorithms or DPP algorithms directly run on a matrix A are fairly slow. And so it's natural to ask, can we get the near optimal guarantees of volume sampling with a faster algorithm? And this leads me to adaptive randomized pivoting. This is an algorithm very recently proposed by Kordanovas and Kushner, which is a very simple and efficient algorithm that achieves the same theoretical guarantees as volume sampling. So this algorithm is going to take as input an orthonormal matrix for which A is approximately QQ transpose A. So the best choice of Q is going to be the top K left singular vectors, UK, but there are also faster alternatives of ways of getting your hands on Q that use sketching. For this talk, we're just going to assume a good Q is given and proceed from that assumption. And the basic idea of adaptive randomized pivoting is don't just directly pick the rows of A, pick the rows of this auxiliary matrix Q. And this is an idea that actually has a long pedigree. It goes all the way back to Golub, Clement, and Stewart in 1976. This also appears in this influential paper of Huckel, Martinson, and Traub. All right, so how are we going to pick representative rows of Q? Well, we're going to use this procedure, which I would call randomly pivoted QR. Also, in fact, due to Deshpande et al. And it proceeds as follows. So I'm going to iterate from I equals 1 to K. And at each step, I'm going to look at the squared row norms of the matrix Q and use them as a sampling distribution to pick a random row SI. And now, once I've picked a row out, well, I don't want to pick that row again, and I don't want to pick any row that's nearly equal to that row. So in order to remove the influence of the selected row, I'm just going to orthogonalize the entire Q matrix against the selected row. And at the end, I'm going to output the set S of rows, which are the random rows I selected during this algorithm. Now, this algorithm is going to run in order nk squared operations, which is very fast. So remember, A is going to be this big data matrix of size n by d, and K is a small subset size. So because the algorithm is only linear in n, this is going to be very efficient. But of course, we always want to go faster. And I'll note for later that this algorithm could be faster because it doesn't leverage block matrix arithmetic. So it can become a computational bottleneck in the algorithm I'm about to tell you. But for now, we're happy with this algorithm. It's linear time in n, and we can use it as a subroutine in this adaptive randomized pivoting algorithm. So this algorithm is quite simple. We begin by obtaining a good orthonormal matrix Q, say by sketching. We then execute randomly pivoted QR on Q to obtain a row subset S. Then Gordon-Novis and Kressner kind of give you some flexibility. You can pick one of two interpolation matrices. So you can pick W1, which will be Q times QS inverse, or you can pick the optimal interpolation matrix, W2, which is equal to A AS pseudo inverse. Now, as I mentioned, this matrix W2 is the optimal interpolation matrix. So it's just a deterministically always true mathematical fact that A minus W2 AS is going to be smaller than A minus W1 AS. Right. And now, Gordon-Novis and Kressner's main theorem is going to give you a bound on this A minus W1 AS. So specifically, they prove that the expected error of A minus W1 AS Frobenius norm squared is equal to K plus 1 times A minus QQ transpose A Frobenius norm squared. And I should emphasize this is an equality, an identity. And if I were to run this algorithm with the optimal choice, Q equals UK, the top K singular vectors, then I get this optimal result where the approximation error, the expected value of the approximation error equals K plus 1 times the best rank K approximation error. And I should again emphasize this is an equality. All right. So as I mentioned, this algorithm is kind of a mix and match. You can make a very fast approximate version, or you can make a more accurate but slower version. So the cheapest way to run this algorithm is to compute this Q matrix using sketching, and then use this cheap interpolation matrix W1, which I again remind you is Q times QS inverse. And the cost of this algorithm is roughly order ND plus NK squared operations. And that's really great because I remind you this matrix A has n times d elements. So if we want any algorithm that looks at the entire matrix A, we have to pay a cost of order ND operations. And then all the rest of the operations are just order NK squared, which is a small post-processing cost. But this is very fast. We love this cheap algorithm. But of course, in many applications, we really care about accuracy first and foremost, and we're willing to pay for it. So in this case, we can compute Q is approximately UK using a more accurate method like block pre-level iteration, and use the optimal interpolation matrix W2. And in this case, the cost is a little bit more, order NK and DK operations. So it's basically K times as expensive as running as just the size of the matrix A. So this is also pretty cheap, but it's more expensive than the first version of the algorithm. All right, so let me summarize the story so far. So adaptive randomized pivoting gives us an efficient way of computing a near optimal subset of rows of a matrix. And seemingly, I've removed volume sampling entirely from the algorithm. However, the practical efficiency of this algorithm is limited by the sequential randomly pivoted QR process. All right. So I know a lot of ideas so far in this talk already. Are there any questions about anything I've talked about up until this point? Awesome. Well, hearing nothing, I'll go on. But again, feel free to interrupt me or post anything in the chat if making sense. All right. Now I'm going to make a hard right turn to talking about an entirely different topic, or a seemingly different topic of active linear regression. So let me begin with a kind of cartoon for what active learning is that many of you have, I'm sure I've already seen. So I'm given some input data, X, is X1 through Xn, which I'll say lives in Rk. And all of the output values, in my case, are unknown. So I don't know what Y1 through Yn are. And my goal is to learn a model that fits the relation mapping X to Y. Now, without any output values, this is clearly an impossible task. I'm going to give the algorithm some information, but only a limited amount. Namely, I'm going to allow the algorithm, or you, the user, to choose a set S of L data points on which I learn the output values Y sub S. Then I ask you, given this set S of data points you chose, now fit for me a model through the data. Now, for this talk, I'm going to focus on active linear regression, where our goal is to learn a linear model. So here, F is parameterized by a set of coefficients beta, and the model evaluated at X is just X transpose times beta. So on the right, I've got a little cartoon of what this looks like. So I begin, I only see the data points X1 through Xn. I don't have any labels. And so I have to pick some chosen points S, which I've indicated by enclosing them in a green circle. And for these and only these chosen points S, you get to see the output labels, YS1 through YSK. And you might ask, you might want to know, oh, what's the value of Y2? Well, 2 is not in our subset S, so I don't get to know what Y2 is. And given only this information that I can see, I now need to fit a linear model F. Right. So hopefully this is a story that many of you have seen before. And it's a very natural question of machine learning and also linear algebra. How do I pick this subset of S? Before I talk about how to pick S, let me mathematize this problem a little bit more. So the input data X1 through Xn, I'm going to collect as rows Xi transpose of a big tall matrix X. I'm going to collect all the responses, even the ones I don't see, into a vector Y of size n. Now, my goal is going to be to minimize the squared loss, the discrepancy between my model and the correct output squared over all data points. And this can be formulated as a matrix linear least squares problem as follows. So I just want to find the vector beta that minimizes the distance between x beta minus y in the 2 norm squared. Now, of course, I can't solve this problem because I don't know all of the entries of y. And indeed, my goal is to identify a subset S of L points, from which then I can solve a subsampled fitting problem where I only am able to sum over the discrepancy between my model and my observed data points, that is the points in the set S. And this again becomes a matrix least squares problem now with matrix X sub S, where again, X sub S is the submatrix of X indexed by S, and YS is the entries of Y indexed by. Now, for this talk, I'm only going to consider the extreme case where I'm only allowed to read L equals K samples. So my data points X lie in RK, and I'm saying I only get K sample. And in this case, the submatrix X sub S is going to be a K by K square matrix. And the solution to this subsampled fitting problem is just going to be beta sub S equals XS inverse times YS. Now, let's turn to the question of how do we pick this subset S? And given the toolbox of things we know how to do already, the natural approach is to use volume sampling. And this approach was proposed and analyzed by Jarosinski and Wormuth 8 years ago. And they showed that if you select S by volume sampling, then the expected least squares residual, where the expectation is taken over all subsets S drawn from the volume sampling distribution, is equal to K plus 1 times the minimum least squares residual over all betas. This is the global least squares residual. And I should emphasize this is an equality in this theorem. And similar to previous parts of the talk, this number K plus 1 is optimal for a worst case instance of the least squares problem, X comma Y. All right, so I've now told you 2 theorems in this talk that look suspiciously similar. So in Portanovas and Kressner's analysis of adaptive randomized pivoting, they proved that the expected error of the algorithm is equal to K plus 1 times the error of projecting A onto Q. I stated that the factor K plus 1 is worst case optimal for row subset selection. And now I have told you another result about active linear regression, where the expected least squares residual of the subsampled solution is again equal to k plus 1 times the optimal least squares residual. And it's very natural to ask, is there a connection between these two results? These two results seem almost too perfectly similar for them to be completely unrelated mathematical facts. And as I discovered, yes, there is actually a connection between these two facts. So let me connect these two facts to you by making two observations. The first is kind of a little bit of a boring technical observation. It's just that this idea of volume sampling continues to hold for multi-response linear regression problems. If I instead want to learn a map from points x and rk to vector valued outputs y and rd, then if I package the xi transpose as rows of x and the yi transpose of rows of now a matrix y, we can again have a least squares fitting problem. And if I subsample down to S rows, I get a subsampled fitting problem with solution B sub S is equal to XS inverse YS. And now we just apply the Dzerzhinsky-Wormuth analysis of active linear regression column by column and use linearity of expectation. Then we can prove that the expected least squares residual with this optimal subsampled least squares coefficients, the expected error is going to be equal to k plus 1 times the best fit for this now multi-response linear regression problem. And I'll just want to draw your attention to this fact. We have an expectation of x times xs inverse times ys minus y. See a very similar expression in a couple slides. Actually, this slide. The second piece of the story is a connection between randomly pivoted QR, the subroutine in adaptive sampling, or sorry, in adaptive randomized pivoting, and volume sampling. So here's a theorem. In effect, it's due to these authors in 2006, although it's been rediscovered many times. It states, let Q be a matrix with orthonormal columns, then randomly pivoted QR on Q samples from the volume sampling distribution. All right, so hopefully the pieces are starting to come together. And to put them together, let us now prove Cordanova's and Kressner's main theorem. So by this proposition at the top of the slide, we know that the subset S in adaptive randomized pivoting, which is obtained by running randomly pivoted QR on Q, is a sample from the volume sampling distribution on Q. Now, if we look at the error in the left-hand side of this expression, we again see a matrix times that matrix subsampled inverse times another matrix subsampled minus that other matrix. And if I just go to the previous slide, you see y minus x xs inverse ys, a minus q qs inverse as. So if I just set y equal to a and x equal to q, then applying this multi-response Dzerzhinsky-Wormuth active linear regression theorem, I compute that the expected value of a minus q qs inverse as is just equal to k plus 1 times the minimum value of this least squares fitting objective. Since Q has orthonormal columns, the optimal B is just Q transpose A. So we string these three sentences together, and I have indeed proved this Cordanova's-Kressner adaptive randomized pivoting theorem as a consequence of this Dzerzhinsky-Wormuth theorem. All right, so let me summarize what we've done at a more conceptual level. Given a good basis matrix Q with orthonormal columns, finding a good subset S of rows amounts to solving a fitting problem where I'm trying to make Q times B as close as possible to A while reading as few rows in the matrix A as possible. And we know that for active linear regression, volume sampling on Q gives us a good way of solving this kind of linear regression problem, where really now we're doing a matrix version of active linear regression where we're trying to bring Q times B as close as possible to A. And indeed, if we use this active linear regression approach, we get approximation to B as QS inverse times X, which is exactly what happens in adaptive randomized pivoting. So a lot of ideas here, but the big idea is that this adaptive randomized pivoting algorithm can just be seen as an instance of using this active linear regression plus volume sampling paradigm from Dzerzhinsky and Wormuth. All right, so why care? So the first reason I care is I think it suggests something kind of deep about the row selection problem. We started off by saying, oh, we have this volume sampling algorithm. It's too expensive. Let's develop this other algorithm. And this other algorithm turns out to just be volume sampling under the hood. And it really suggests to me that, in some sense, the volume sampling idea is fundamental to optimal algorithms for row subset select. So that's an interesting point to me. May or may not be interesting to you. But I think the second point is even more convincing, is that the speed of adaptive randomized pivoting is limited by the sequential randomly pivoted QR step. And by noticing this connection between adaptive randomized pivoting and volume sampling, we can use fast rejection sampling based volume samplers to speed up the adaptive randomized pivoting algorithm. And I'll now tell you a little bit about that. So let me start off by heading off a possible point of concern or a misconception. So I began the talk by telling you that volume sampling is very computationally expensive, and this is true. So if I have a big data matrix that's wide, it's pretty hard to do volume sampling on A. But in this case, we want to do volume sampling on a tall, thin matrix Q. And this is actually a pretty easy problem. And in fact, we have an extra piece of information that Q has orthonormal columns. And this makes the volume sampling problem extra easy in some sense. So we're going to leverage this fact that volume sampling on a matrix with orthonormal columns is super easy. And let me tell you about that. All right, so randomly pivoted QR, this main subroutine in adaptive randomized pivoting, is very sequential. So this algorithm, at every step, it selects a single row of the matrix, which is a tiny fraction of the matrix, and then it orthogonalizes the entire matrix against one single row. And so this is expensive for two reasons. First, it updates the entire matrix, and two, it updates the entire matrix by orthogonalizing only against a single row. And modern computer processors are much more efficient at dealing with blocks of rows rather than single rows. So it's natural to ask, can we avoid updating the entire matrix, and can we batch the updates? And we can do both of these things. Here's the first trick. We're going to not update the entire matrix. So this is an idea for a fast rejection sampling based volume sampler by Dzerzhinsky et al. In 2019, and it was discovered by another set of authors in 2023. And here's the idea. So instead of orthogonalizing against the entire matrix at every step, we're instead just going to maintain an orthonormal basis for the already selected rows. Then we're going to use rejection sampling. But here's what I mean. So we're going to begin by doing squared row norm sampling. So we're going to pick a random proposal row with probability proportional to the squared row norms of the matrix Q. And I emphasize in this algorithm, we're not going to update the matrix Q at all. So these are the squared row norms of the original matrix Q. Now we're going to orthogonalize the selected row against all of the previously selected rows. And then we have a choice. Do we want to pick P as a new element of our subset, or do we want to throw it away? And in order to decide whether to do this, we're going to accept with a probability, which is given by the size of this row after projection normalized by its original size. So with this acceptance probability, we're going to accept and pick the proposal row, and we're going to set it to be our new ith element of our subset and increment our counter, and then update the basis matrix Q to contain the new newly orthogonalized row. And if we get the complementary event, if this we don't accept, then we're just going to go back to one and pick another proposal. And this algorithm is very simple to analyze. I won't show it on the slides, but basically we can prove that with high probability, only order k log k loop iterations are needed for this procedure to terminate, each step requires order k-squared operations, so the total cost is order nk plus k cubed log k operations. And this is going to be wicked fast for most problems. Now, this algorithm avoids updating the whole Q matrix at every iteration, which is a big improvement, but it still processes one proposal at a time, which is not as efficient as it could be. I proposed a modification of this algorithm that processes blocks of proposals all at once, which uses matrix operations and is much faster on modern hardware. And to give you a sense of the kind of speed upgrades that we've obtained by using this approach, the basic unaccelerated randomly pivoted QR algorithm takes 43 seconds to run on a model problem. And using this new fast volume sampler with the block matrix computations, it takes just 0.12 seconds. So it's a speed up of 350 times. And by using this fast volume sampler, we've now taken the bottleneck step of this algorithm, the slowest rate limiting step, this randomly pivoted QR, and we've replaced it by by a new subroutine, which is now the fastest in this entire algorithm. So we've really, really sped up this bottleneck operation. And there's one more bottleneck that we can speed up. So this matrix W2 often gives more accurate approximations than W1 because it's the optimal approximation, but it can be significantly more costly. So we can accelerate this by using a second level of sketching, which I've shown here. The details are not important. Again, this just leads to big speed ups. So we have a 3.7 times speed up over the optimal interpolation. And as we'll see, it gives nearly the same accuracy. All right, so I understand I'm running up against time, but let me just briefly show a couple numerical experiments. So I'm comparing different versions of adaptive randomized pivoting against some baseline methods from the literature. And let me show the results. Here's first a speed experiment on a dense matrix. And you see this Kordanovas-Kressner implementation of adaptive randomized pivoting is really slow because it uses the slow randomly pivoted QR subroutine. But by replacing it with this much faster fast volume sampling, we really cut down the time. And indeed, the adaptive randomized pivoting methods with these fast volume sampling implementations are now the fastest algorithms among a subset of methods, and we achieve a 17 times speed up over the original ARP algorithm. And these speedups persist to sparse data matrices as well. We now get a 23x speed up over the original ARP algorithm. Now, of course, we don't just care about speed, we care about accuracy. So here's a scientific data analysis problem involving some genetics data. So we see that this ARP algorithm with this cheap interpolation matrix W1 is basically totally useless. But if we use the optimal interpolation W2 or the sketched interpolation, we get much better accuracy. And I'll note that we achieve the same accuracies as slower baseline method. Now here's more of a scientific computing example. We have a Coulomb interaction matrix. And I'm showing all 5 methods. And you see that all methods are converging at the same geometric rate, but the ARP methods are the fastest. We achieve the same accuracy up to some multiplicative error as the other methods, but we are much faster. So this is, again, I think also a nice demonstration of this ARP algorithm. All right, a lot of material. Let me summarize. Adaptive randomized pivoting is one of the most effective algorithms for row or column subset selection. And as we've seen, this algorithm has close connections to active linear regression and volume sampling / determinantal point process sampling. And by leveraging these connections between adaptive randomized pivoting and volume sampling and active linear regression, we have made the algorithm significantly faster. In particular, using the optimized implementations developed in this work, adaptive randomized pivoting is among the fastest and most accurate algorithms for row subset selection. So with that, I'd like to thank you all for your attention. I'd be happy to answer any questions.
Wonderful. Thank you, Ethan. I'll stop the recording and then we'll take some questions.